Warm greetings to all the participants. In the previous board, we discussed interpolation and the relationship between the pixels. And in this board, we are discussing distance measures. It means suppose we have a P point image in the P and Q image, 2 pixels we have suppose, then what is the distance between, how we are measuring the distance between P and the Q. Okay, so here suppose given pixels are P and Q and Z. For the discussing how to measure the distance, here for the sample we taken 3 pixels P, Q and Z. Each pixel having coordinate. So the P pixel is having the coordinates x, y. This is the P pixel coordinate. And the Q pixel coordinates are s, t. This is the Q pixel coordinate. And for the Z pixel, the coordinates are u, v. This is the Z pixel coordinates. Okay. Then now we have a function which is measuring the distance, that is represented with the letter d. So distance function is here the d. It is denoted with the d. Then this distance measures function having 3 properties. The first property is distance of p, q, okay, is greater than or equivalent to 0. This is the first property, the distance function having. It means whenever the p is equal to q, when we are having p is equal to q, if there is a distance between the p and the q, then we can measure from p to q by applying, by using some mathematical models like that. Then if suppose p is equal to q means there is no distance. So the distance function p, q is equal to 0 at that time. Okay, when it is 0 distance function, whenever, if and only if p is equal to q. And always in remaining situations, the distance function p, q is always greater than or equal to 0. If it is 0, it means p is equal to q. There is no distance between p and q. There is no second pixel. There is a single pixel. And the second property of distance function is distance of p, q is equivalent to distance of q, p. It means what is the distance we have from P to Q is similar distance again we have from Q to V. This is the another property. And next, the distance of P, Z is less than or equivalent to distance of P, Q plus distance of Q, Z. The distance measured between 3 pixels. Okay, so this is the distance function, and these are the properties of distance function. And then how we are measuring the distance measures, how we are measuring. For that, the DIP using earlier Euclidean distance, it is using to measure the distance between the pixels. So we know P, we are measuring the distance P and Q between P and Q. So the distance function is D. Then Euclidean distance formula is saying, defining x minus s whole square plus y minus t whole square whole to the power of 1 by 2. Okay. So this is the formula for the Euclidean distance between 2 points. Here 2 points are 2 pixels P, Q, and for the P pixel the coordinate is x and y, and for the q pixel, q point, the coordinates are s and the t. So this is the formula. And another distance measure we have method we have is the city block distance. Within this city block distance, the distance function formula is mod of x minus s plus mod of y minus t, absolute values. Okay, and if we are applying the city block distance upon two pixels, 2 points with the coordinates x comma y and s comma t respectively, then this, for example, this is the sample image we will get. And another method for the distance measure is the chessboard distance. Within chessboard distance, the formula to calculate the distance, we are measuring the distance using chessboard distance is max function. It is max function, max of mod of x minus s comma y minus t, absolute values. And if we are applying chessboard distance, then this is the resultant image, for example, we will see. So city block means the appearance of the image values look like this in this pattern, and for the chessboard we will get the output of the image, digital image in this pattern. And now these are the different distance measures methods we are applying: Euclidean distance, city block distance, chessboard distance. And now coming to the mathematical operations, we are using basic mathematical operations in digital image processing. So here we are taking array operations, matrix operations. So for example, we are taking two matrices, A matrix and the B matrix. Okay, then these are the values within the elements within the matrix, A matrix, and these are the values in the B matrix. And now if they are calculating the array product of array for the array, okay, then the product of array resulting the values A11, B11, okay, and A12, B12, and here A21, B21, the product of these two, and A22, product of B22. In this way, so this is product with this, and this is product with this, and this is product with this, and this is product with this. In this way, array product is calculated. And for the matrix product operation, this you will know easily. You did so many times this operation, matrix product operation. This is A11, B11 plus the horizontal multiplication with the column multiplication. A11, B11 plus A12, B21 in this way. A11, B11 plus A12, B21 in this way. So in this way, matrix product we will calculate. And then what are the arithmetic operations we are using in the digital image processing? So here the arithmetic operations we are applying upon array operations. Okay, so between images, array we are applying array operations. We have four arithmetic operations. Those are, suppose s of x comma y is equal to f of x comma y plus g of x comma y. Okay, this is the plus operation. And next is the same minus or subtraction operation. and next is the multiplication operation, and next is the division operation. These are the four basic arithmetic operations we are applying upon in array operations. So we have seen basic arithmetic operations upon arrays of the images. Then, for example, how we are applying, where we are applying in the digital image processing. Suppose here I'll show an example. Addition of noisy images for noise reduction. If there is included a noise within the originally captured image, then how we are removing the noise? Noise reduction happens how? Okay. Then suppose images noiseless image is represented with the f of x comma y. Okay. Then the noise is represented with the n, and the coordinates for that one is also x comma y, because for that particular coordinates we are uh, reducing the noise. Okay. So noise n of x comma y, these pair of coordinates, the noise is uncorrelated and has zero average value. Okay. Suppose take the corrupted image. The corrupted image is represented with the z of x comma y. Then our noiseless image is adding with the noise n of x comma y. This is the noiseless image f of x comma y, and this is the noise n of x comma y. Noise is representing, denoting with the n. Okay. Then how we are reducing the noise? By adding set of noisy images. Set of noisy images means this is the corrupted image, means this is the noisy image. Okay. Then set of noisy images means within the set is represented with the curly braces. Then set of means how many we don't know the index values, 1, 2, 3, and so on. We are generally representing with the I. So g of I x comma y is a noisy image. By adding these set of images, okay, then we are getting a reduced noise image, noiseless image. This is represented with the g dash of x comma y. So we are applying, adding set of, so addition means it is the sum of. So the sum of is the sigma of I is equal to 1 to k. Okay. Then g of I of x comma y. We are adding all these. In this way, we are addition of noisy images for noise reduction. In this way, we are doing. And then other mathematical operations in the digital image processing, we are applying other mathematical operations are linear, non-linear operations. What are linear and non-linear operations? So, suppose linear operations means they are the linear transformations satisfy some properties. Okay, some properties it is satisfying the linear transformations, linear operations. What are those properties the linear transformation, linear operation satisfying? As the additivity and the homogeneity. These two operations are satisfied, then it is a linear transformation. And suppose these two operations properties are not satisfied, then that is a non-linear operation. So here see, for example, linear system. What is defined, the definition of the linear system? whether a system is linear. To see, we need to test whether it obeys certain rules. Okay. What are those rules and what the linear system obeying? The two basic tests of linearity are homogeneity and the additivity. These two rules we have to test, and if these two rules are obeyed, then it is a linear system. Then what is homogeneity? Homogeneity means uh, suppose we are increasing the strength of a simple input. How we can increase the strength of a simple input? By multiplying it with some weight, with a constant. For the input value, we are multiplying with a constant. We are calling it as a weight. Then we are doubling it. The system, the input value is doubling it. Then we are predicting that the output function and, and it will also be doubled. And here I'll give an example for the homogeneity. Suppose a person is there, and if a person's voice becomes twice as loud, okay, then the ear should respond twice as much. It's as much. So the ear is responding twice. It means the system is linear system, and this is called the homogeneity. And we are also sometimes we are also call it as a scalar rule. Scalar rule of a linear system. Okay? And I'll show the example picture for the homogeneity. The scalar rule here. This is the original image. Okay? In this time it is taken. Then this is the multiplied with the two doubled image. Then the original image became this. So for this original image, the output is this electrical activity, and for this doubled one, then the predicted output is this one. The output is also doubled. This is the homogeneity. Then coming to the additivity rule of the linear property. See here. Suppose we present S1 sound of a person voice to the inner ear. We are giving S1 as the sound to the inner ear, person voice. It is a person voice, and we are measuring that one with the electrical responses. The for several nerve fibers coming from the inner ear. All these we are measuring. And next we are presenting second S2 voice, a little different voice to a different person voice. Okay, then the second stimulus also generates a set of responses, electrical responses. We also measure those one and write down those one. So first we taken S1 and then taken S2 voice, two different persons' voices to the ear, and we uh, observed and calculated the electrical responses of several nerve fibers coming from the inner ear. Then we present the sum of the S1 plus S2. Then we see what will happen. We are presenting both voices together and see what happens. Then if we applied the additivity, then it is the linear system. So if it is the linear system, then the measured responses will be just the sum of its responses to each of the two stimuli presented separately. So the linear system is presenting both the stimulus results. I'll show with the diagram example. This is the additivity property. In this, the first input, here suppose we taken S1 voice, then for this corresponding predictive output is this one, and this is S2 voice, second input to the same ear, inner ear. Then this is the, for this S2, this is the predictive output. Then here we combined S1 and S2. Then this is the resultant one. See here, the S1 is uh, added with the S2, that is represented with the dotted lines here. You can observe here. Okay. And then in the image processing, the linear was nonlinear operation is defined as h of f of x comma y is equivalent to g of x comma y. Then we are applied some constant, we multiplied with some constant. Then this is the equation for the additivity, and this is the equation for the homogeneity, and this is the resultant one. Then this, if these two are satisfied, then this is the linear operation. Otherwise, if these two are not satisfied, then it is a non-linear operator. So, we have seen the example addition of noise images for noise reduction. So, where we use this noise reduction and addition of noisy images for noise reduction, how we are applying, where we are applying means, here I am showing an example. In the astronomy, the maximum they are using these kind of noise reductions by adding noisy images. Okay, so in astronomy, imaging under very low light levels frequently causes sensor noises, and to render single images virtually useless for analysis. So in this way, with the sensor noises, uh, a single image in the single image we cannot within the single image, within that we cannot analyze any kind of predictions and any kind of analysis. We cannot get any output from that. Okay. Then by the astronomical observations, the similar sensors for noise reduction by observing the same scene over long periods of time. Okay. Then image averaging is then used to reduce the noise. In this way, in this way we are using, and this is the major application to reduce the noise, and this is the major application where we need to reduce the noise by adding noisy images. And here it is an example, and this is the image of the galaxy, and these are the results of the averaging images. By these noisy images, in these images a noise is included, then by these we cannot predict the values, we cannot predict the analysis, and these images are taken by the NASA. And now an example for the image subtraction. For the image subtraction, a best example is mask mode radiography. Within this, we are maximum using image subtraction. So, mask mode radiography means here we are applying mask, the H function mask, and an X-ray image of a region of a patient's body. So here live image is represented with the f of x comma y, we know this, and X-ray image is captured at TV rates after injection of the contrast medium. Then after applying the masked image upon the original image, live image, then enhanced details we will get that is denoted with the g of x comma y, this we know. So the g of x comma y is the original live image f of x comma y minus the mask h of x comma y. We are subtracting the mask. So the procedure gives a movie showing how the contrast medium propagates through the various arteries in the area being observed. This is the example for the subtraction. This is the mask and this is the original image. We are applying some subtractions. These are the resultant images and this is the final g of x comma y. And now this is the example for the image multiplication. This is the captured image and we are multiplying with this image. This is the resultant image. And now set and logical operations. We know this. A set A is there and second set B is there. Then the union of A union B is the total area of these two sets. And the intersection of A intersection B is only the common area between A and B. And the complement of A means A is not included within the total resultant set. Excluding the A is A complement and A minus B means we are taking only A elements and even we are not taking the common elements of A and B. Now set and logical operations. So here the set and logical operations, we know very well this. Let A be the element of a grayscale image. Then elements of A are triplets here. Means the form of triplet is x comma y comma z, 3 coordinates, and where x and y are spatial coordinates and z denoting the intensity value. Okay. Then at the point x comma y, the set A is defined x. The set A is defined as x comma y comma z such that z is equal to f of x comma y, the intensity value of the z. This is the set definition for grayscale image. We are denoting the grayscale image with the A here. Now the complement of A we can define as the set of x comma y comma k minus z here such that x comma y comma z as belongs to A and the value of k here is 2 power k minus 1 where k is the number of intensity bits used to represent the z intensity value. Next set and logical operations are the union operation You know very well about this too. So union of two grayscale images means two sets A and B are defined as A union B. So this is maximum of Z of A comma B such that A belongs to A and the B belongs to B. This is the definition for the union of two grayscale images. By using this model, we will union two grayscale images. Then see, this is the example for the set and logical operations just we discussed. This is the original image. Okay, suppose the A grayscale image, and this is the complement of A image, the negative of A image, A complement. Now this is the union of A image with the A complement image. Now the set and logical operations takes place like this. So here the white area is giving the foreground of the logical operation. So this is the set A, and if we are applying the not logical operation, then this is the output. And if we take in two sets A and B, then the end logical operation giving this output. Now for these two, OR is giving the OR operation is giving the output this one. You know, OR is a OR of logical operation, and the AND NOT giving the output this one, and the XOR operation giving the output this one. So in this board, we covered the topics distance measures and the Euclidean board, mathematical operations, arithmetic operations, and we have seen an example for addition of noise to reduce the noise and subtraction of noise. We discussed linear and non-linearity of the images and set and operations and set and logical operations we discussed, and uh, for in the next board we will discuss spatial and Fourier transformation operations. Okay, uh, thank you.